and everything. So everybody can, yeah, okay, good. So I found very funny that everybody was changing the virtual background to the place where they are. And I thought of taking a picture of the outside of the lab because we are in a very beautiful lab. But it turns out that the weather this summer in Paris is awful. So I decided to put something that I consider even more beautiful. There is the inside of our lab. So if the postdoc doesn't move for 1 hour, don't be scared. He's just in a picture. So today, I would like to talk about topologically valid states in graphene BN systems. So I consider this to be a very good example of a topological state that is developed in a very simple system. This is just the first version, or the first part of this talk, that is today's talk, is just the monolayer version. And tomorrow we're going to see the bilayer, a little bit more complicated version. So I consider this a very extremely simple system. It's just graphene on boronitride, aligned on boronitride, and turns out to be, for me, a very beautiful example of topological states. So before starting, why do we want to do this valid states in graphene? Well, we all know that we are always looking for new states of matter that will hopefully one day become applications or technological developments. In our case, we focalize on valid states because valid states in graphene are very robust, given the large space in momentum, the large separation in momentum space of the two values of graphene, so inter-valley scattering is reduced. In this, using this kind of systems, we can develop what is the future, we hope it will be, the future ballitronics devices. So, of course, I know you all have seen this thousands of times, but I really need it in order to know that everybody is starting from the same point. So graphene, you know this very well. It's an hexagonal lattice of carbon atoms where we have two sublattices, A and B, as you can see here. It's Brillouin zone is also an hexagon, and we have two equivalent points in the at the corners of this Brillouin zone. Its electronic band structure is something that by now we all know by heart. It's a linear energy dispersion, and these two Dirac cones touch to each other at the K and K prime points. In these are, of course, what we were talking about, the valleys. Now, as an experimentalist, if I'm going to talk about anything, I'm going to show you also an experiment that goes with, or that at least I consider that is a good example of it. So if we take just a layer of graphene, I hope you can all see my mouse. So if we just take a layer of graphene, as we did so many years ago on silicon oxide, and we connect it electrically, we pass a current through it, and we measure the voltage drop across. And we use, of course, this graphene is deposited on an insulator, which has a highly conductive silicon layer underneath, and we can apply a gate voltage. So if we do this, we are able to tune the Fermi energy of the system. We can see in here that the resistance as a function of the gate will strongly increase at the charge neutrality point, and then it will decrease. In fact, I think Pablo already mentioned this, but why not to repeat it? In fact, this is one of the most interesting characteristics of graphene in terms of future applications, is the fact that we can change the nature of the carriers. We can pass from a conduction of electrons to a conduction of holes. But of course, this electronic band structure has other characteristics that are also important. For example, we have a Berry phase of pi. So let me just remind you that a bare phase is this additional phase that the electron carries on once it finishes an arm. So now the clearest example of these consequences of the pi bare phase of graphene, and let's say that the one that is the more dearest to my heart is the formation of Landau level, how the Landau level spectrum will change, will be modified by this pi bare phase. So one of its characteristics is the formation of the n equals 0 Landau levels, one of the most clear characteristics in the Landau level spectrum. So just to know that we are all in the same page, when I talk about the quantum Hall effect, let's say the best example, we all get it when we talk about conventional two-dimensional electron gases with parabolic bands. We apply a magnetic field, and we can see, that the energy is split in levels. These are called the Landau levels. In the case of a two-dimensional electron gas, these Landau levels are equally spaced. Now, of course, what happened in an experiment? So if we take a whole bar of a conventional, made in a conventional two-dimensional electron gas, we pass a current and we measure the voltage drop at both parts, we will see in this wonderful Wikipedia animation the formation of Landau levels, and at the same time, what we have in the longitudinal resistance is oscillations of the longitudinal resistance and a quantization of the values of the transverse resistance. So this is due to the formation of chiral edge states along our sample. So this quantization of the Landau levels, this quantization of the transverse resistance, it's so well quantized. In fact, it depends only on fundamental constants of nature, as Planck's constant and electron charge. So this is such a good value, it's such a robust effect that in fact it has been used as a practical electrical resistance standard of the International System of Units since the 90s. But when we talk about graphene, as I told you before, things change. So this linear energy dispersion of graphene and this pi bare phase will have strong consequences, and you can see the difference between the Landau level formation of all systems. So, as I told you before, the first will be the n equal to 0 Landau level, and then we also have the fact that the Landau levels are not equally spaced anymore. This gives you some advantages, like, for example, the spacement between the two first Landau levels is much greater than in the case of gallium arsenide or other conventional two-dimensional electron gases. So, in general, what we can say between these two is that we have the same phenomenology. We have edge states for both, but we have very different responses. So this is so different, in fact, that if we just plot the spacing between the two first Landau levels for monolayer graphene and for gallium arsenide, we can see that they are very far apart. But not just that, we can look at it from the metrological point of view. For example, if we do that, we know that this spacement between the Landau levels should be much greater than the temperature of the measurement in order to obtain a good, an accurate 1 part in a billion quantization. And just with this very quick calculation, we can see that, in fact, graphene is expected to have a very accurate quantization much lower than 1 Tesla. Very different to, for example, gallium arsenide, which is about 10 Tesla right now. And this made of this topological state in graphene one of the most promising new quantum Hall resistance standards in the world. And so that in 2015, we made some accuracy measurements on graphene, and using just CVD graphene grow on silicon carbide. So, and we could see that in fact, this 10 to the minus 9 accuracy of graphene can be obtained for magnetic fields as low as 4 Tesla. And in fact, they span all over 14 Tesla. And in fact, we made no accuracy measurements, but just transfer measurements from 14 Tesla to 60 Tesla. And the plateau was still there. So there's a lot of things to study in the system, because an infinite plateau is something that we haven't seen before. This might be probably related to contributions of the substrate, but nevertheless, it's a quite remarkable physical property. So you can start to see already that the range of magnetic field for graphene is much larger than the one of gallium arsenide, which is only 1 Tesla, around 11 Tesla. So, but we are still quite far. No, this is not what I was promised. I was promised less than 1 Tesla, and we are at 4. So we still have a lot of work to do. But fortunately, we can still use this as the new quantum Hall resistance standard in the world, in metrology labs right now. And more promising is that the new experiments that we are performing right now on encapsulated graphene allow us to see quantize. We don't know yet how well, because the accuracy measurements are very, very long. But quantize Hall resistance, so quantum standards, at 285 millitesla and 5 Kelvin, which is quite remarkable. I know this, it's maybe not numbers that says something to everybody, but it's quite remarkable that we can observe quantum Hall effect, well-quantized quantum Hall effect at such a low magnetic fields. And when I'm saying this, I also want to emphasize that all the beautiful physics that we have been seeing all over this week, and that I hope I'm going to show you next, it's because a tremendous amount of effort has been put into improving our samples of graphene. So, for example, a long time ago, the first measurements of the quantum Hall effect in graphene on silicon oxide, just at 14 Tesla, they show the integer quantum Hall effect, but nothing else, no signatures of breaking of the genesis, or not even dreaming of the fractional quantum Hall effect. Later, in 2010, with the first fabrication of van der Waals heterostructures, we came to observe finally the first breaking of the genesis in the Landau levels of graphene. So just as a reminder, each Landau level in graphene, it's composed of 4 states, 2 for spin and 2 for valley. As you increase the magnetic field, if the splitting between the Landau levels overcomes the disorder on your level, then you start to see these splittings of the energy levels again. So we could reach at the same magnetic field and same temperature. I forgot to mark that. We could start to see already the formation of the lifting of the degeneracies. Now, more recently, we have been able to make what I will describe as the probably most beautiful and most complicated before the twisted tri-layer sample appear. So this, for example, this van der Waals heterostructure shows quantized in fact, not quantized, it shows Landau level formation. This is a Corvino. Landau level formation from 100 millitesla. So this is a Corvino sample. In fact, we are only testing the bulk of the system. And it's really a marvelous job. It's made with 2 graphite gates. It's really one of the best things you are going to ever see. So this is very good. So we have come all this long. We have the samples of the quality we want, but we need new things from graphene. So graphene, it's a gapless semiconductor, and we need a gap. Why do we need a gap? We need a gap because when we open a gap in graphene, we break inversion symmetry, and this inversion symmetry will allow us to access topological properties such as the Berry curvature of the system. I'm going to talk about that just in a sec. So by the way, if you have any questions, just ask. I have the questions and response somewhere. So if we want to open an energy gap, let's say that the easiest way we know in graphene, or in the cleanest, one of the cleanest way we know in monolayer graphene is to align it with boronitride. So when we align graphene and boronitride on top of each other, a moire pattern develops. I think you have here a little bit of that in the last week. So this moire pattern, in fact, has a relation. It has a maximum size of 14 nanometers. It has a strong relation with alignment between the layers. It's very important to remark that almost every property in twisted systems, it's strongly dependent on the angle. I think you are very well aware of this because of Pablo's and the other talks that we had today and the last week. But it's very important to keep in mind that sometimes having 0.2 degrees is not the same as having 0.8 degrees. So now, this moire pattern can be observed directly in scanning tunneling microscope measurements. They have been able to really measure different moire patterns and characterize their electronic structure, the electronic properties of this system. But as I do electronic transport, I'm going to show you what are the consequences or what are the effects of this moire pattern, the modification of this electronic band structure, mainly using transport techniques. So once again, let's imagine that we have our device, we pass current through it, and we measure longitudinal or local resistance. So in the case of just graphene at 30 degrees with BN, so they are not at all aligned, they are as far as they could be of alignment, we still have this or something very close to this linear energy dispersion. So if we use our electrostatic gate to tune this Fermi energy, we will once again find a resistance peak that increases, or resistance that increases at the charge neutrality point. Now, if we take the same two layers and we rotate them, and we put it to 0 degrees, we're going to observe, as I told you before, this moire pattern that superimposes to the whole, just give me a second. What is the pattern of graphene and BN at 0 degrees rotation between the layers? What is the pattern? Lattice, do they not fully overlap like two? Yes, okay, so there's a question that says, what is the pattern of graphene and BN at 0 degrees rotation between the layers? As they are different lattices, do they not fully overlap like two layers of graphene? So yes, no, they have a difference of 1.7%. In fact, graphene and BN, when they are fully aligned, you see this moire pattern. That is the same that I show in the STM measurements. Now, there is something very important and that might change everything here. When graphene and BN, they are completely aligned. We are really at 0 degrees. Some STM measurements show that there is a formation of solitons. So in fact, what happens is that in what is the center of the moire, like here, graphene will stretch to match the lattice constant of boron nitride, and then it will release that strain. And where it releases this strain, you will have corrugations of graphene. And these corrugations, or also called solitons, they will form these hexagonal shapes here. Okay, hope that answers the question. So where I was? So now I align graphene on Bn, and I'm gonna change the Fermi energy in the same way as before with an electrostatic gate. Now I know that there are some modifications in the electronic band structure. We have the appearance of these satellite peaks, which are just the consequence of the folding of the bands, and we have the opening of a gap at the charge neutrality point, which is the consequence of breaking inversion symmetry. Now, if we measure as a function of this change in the Fermi energy, or this applying a gate, changing the carrier density, so we will see when we cross the first, the satellite peaks, we will see a first peak in the resistance. Just a second. Sorry. And we are also going to see a very slight increase at the charge neutrality point. So, of course, this very small increase cannot be compared to an energy gap, cannot be addressed as an energy gap, but I would like you to keep an eye on the fact that this experiment is made at 300 K. So this, it's just room temperature. This is remarkable in itself because we can see the modifications of an electronic band structure even at the room temperature, but there is no way we can compare the size of this gap with room temperature. So that's why we don't see a higher increase in the resistance. Now, since we are measuring transport, and we developed this technique a few years ago that allow us to control dynamically the rotation between two layers of graphene. So what's happening here is that we have a layer of graphene in a hole bar shape on the bottom. We are measuring the voltage and we're passing a current in a longitudinal way. We're going to take an atomic force microscope and we are going to move this capping layer of hexagonal boron nitride that has been pre-shaped. So that will allow us, in fact, to modify in situ the electronic band structure. So these three AFM images here show an exaggeration of the angle because we are not working at 45 degrees of rotation. We are only making very, very small rotations. So those small rotations will allow us, in fact, to see what's the full span, the full spectrum of changes, of how it changes completely the band structure, how we can move and position this satellite peak to the energy that we would like. So now, since we are measuring electronic transport, we are able to also extract the energy gap. For example, in this case, I'm showing you the thermal activation curves for the satellite peak from room temperature to 1.5 K. So we did this for the satellite peak and the charge neutrality point, and for as many angles as we could. And what we observe is we have a satellite peak that behaves in a fashion that we can explain very well. It means that as you go away from the line position, this gap closes. As you go in, the gaps increases. But the gap at the charge neutrality point seems to have some sort of oscillatory behavior. Or in fact, at the beginning, it seems more like a random behavior. But in fact, if you have a look of some points like this one, where we have a field and an empty spot, that means that we measure first that angle, then we went to a different angle, and then we came back to this one. And we measure exactly the same value within the error bars. So this oscillatory behavior is there, but we don't know how to explain it yet. So if we compare these values, these gaps, with what has been predicted in theory for what has been predicted in the simulations of this electronic band structure, we can see that, in fact, the satellite peak is remarkably close to what has been predicted. But contrary to that, the charge neutrality point it's much larger than what was predicted before. But it's also in good agreement with other experimental measurements. So we don't really know what is missing in the numerical simulations for this, to obtain the good values of the energy gap. But now, then, if we have our band structure that has been modified, then we have the opening of the gap at the charge neutrality point, for example, we can now have access to the value of the Berry curvature, which we didn't have access before because the system had time reversal symmetry and spatial inversion symmetry. Now, by adding the BN and aligning the two systems, we got rid of the spatial inversion symmetry, and we finally get access to this Berry curvature. Now, what will happen with when this Berry curvature is not zero anymore? What will happen here is that this will give to the carriers an anomalous velocity, and this anomalous velocity, importantly, will be opposite in each valley. Okay, so maybe this is a super naive cartoon, but I like a lot the fact that it's very clear. If you have a carrier in your valley K and one in your valley K prime, and you apply an electric field, then they will move in opposite directions. So now if you see this corrected velocity, and you see the expression of the Lorentz force, or what happens when you apply a magnetic field to a two-dimensional electron gas, you can see that they resemble a lot. So in analogy with the magnetic field, this Berry curvature is viewed as the magnetic field in the momentum space, okay? And a straightforward consequence of having this Berry curvature is an induced Hall conductivity. This induced Hall conductivity, in the case of monolayer graphene, will have a value inside the energy gap. Remember that if you do not have an energy gap, you cannot have Berry curvature. So inside the energy gap, it will be quantized as 2 squared over h, and outside it will decrease very rapidly with the Fermi energy. So this is good. So it means that it not just exists, but we could maybe measure something that gives us access to this. But in fact, this valley Hall conductivity, it's not something that we can directly observe. It's not something that we can directly measure. But fortunately, we have values that we can measure. The valley states are valley momentum locking. The effect here in monolayer looks like the kink states due to the, sorry, I'm reading my question. I think that valley states are valley momentum locking. The effect here in monolayer looks like the kink states due to the inversion in electric field. I'm not sure I understand the question, so I'm just gonna keep it there. And when I finish, I'm gonna come back to see if we can, if I can understand what it says, okay? I'm sorry about that. So, unfortunately, we cannot have access to this valley Hall conductivity, but there is another quantity that we can have access to that is closely related to this valley Hall, that is the non-local resistance. So in this expression, we just have the non-local resistance, and I'm going to explain you just in a second how to measure it. the width of the sample, a characteristic length of the K length of this valley current, the local conductivity, and the length of the system. So everything can be measured, and it's very easy accessible, and it has at least a meaning in the way these currents will propagate. So now let's say, once again, let's take our device and see what we can measure here. So non-local voltages or non-local resistance are measured in the following way. We're going to apply a current between these two leads, okay? So normally, without any Berry curvature, the carriers should go from this electrode to this electrode just straight ahead. They should not deviate. Now, thanks to the Berry curvature, electrons or carriers belonging to one valley, let's say valley blue and valley red, I'm just going to relabel it like this because K and K prime might be a little bit confusing. Okay, so carriers in the valley blue will move to the right, while the ones in red will move to the left. And this is what we call the valley Hall effect. This is splitting of the valleys moving in different directions. It's the same that happens, for example, in materials with a strong spin orbit coupling, where you have the spintronic devices, where you have a spin separation. It's exactly the same effect, but this time with pseudo spin, that is the valley. And in the other side of the device, what you will have is the inverse valley Hall effect. So now your carriers will accumulate in one of these electrodes. Okay? I hope that was clear. So now the first measurements about this were performed in 2014 by the Manchester group. I'm going to try to go step by step because this might be a little bit confusing on some experiment. So the first part is just, we're going to apply a current through our devices and going to measure the voltage. So this is just measuring the same resistance that we have been explaining since the beginning, okay? So we see the main peak, charge neutrality point, satellite peak. We already know this. Now we are going to do also a non-local transport measurement, okay? We're going to apply the current in this direction, and we're going to measure the voltage between these two. If there is some splitting of the currents, of the valley currents, then we should see some non-local voltage. If there is no splitting of the valley currents, we should not see any non-local voltage because our electrons, our carriers, will just continue straight. Of course, here you have some small things that you have to consider. You also have, if you are in a ballistic regime, for example, the electrons will dissipate, will not just go straight as good carriers going very straight. And you will have what's called an ohmic contribution. Okay? But we are going to just see what they did about this in a second. So now, they measure this non-local resistance. Turns out that they observe two strong peaks of non-local resistance, one at the charge neutrality point and the another one at the satellite peak. So these two corresponds to the Berry curvature hotspots that we have in the electronic band structure. Notice that at the electron side, in this measurement, there is no even a small sign of a change in the non-local measurement. And this comes from the fact that there is no opening of the gap in the satellite peak that is in the electron dope regime. So now, keep in mind for the future, for the next slides, that the maximum of resistance that they observe, it's about 600 ohms, only 600 ohms. Okay, so it's also very challenging as an experiment because these are very low resistance. So if we have a look more closely to this region, to the region of the charge neutrality point, And we compare, for example, this local resistance in green. The red is the non-local resistance multiplied by 20, is 20 times the real value. And they compare directly with the non-local resistance of a non-aligned device, okay? And of course, they calculate also what's the ohmic contribution that this local resistance should have using just the van der Pol relation, which is much smaller than the 600 ohms that I told you before. And okay, well, they see a signal. This doesn't really explain if it's topological or not topological or what is happening here. Now, if they replot the data as a function of the density, and they could observe that the local and the non-local signals, they have a completely different dependence. The local resistance has a dependence of 1 over n, so 1 over the density, while the non-local resistance, in fact, it has a dependence that goes as, that has a cubic relation with the local resistance. And this, if you remember from the beginning, is what I show you that we could measure. We could measure the sorry, I'm just gonna go back and show you again. I told you that we cannot access this valley hole conductivity, but fortunately, we can access this non-local resistance, which will give us eventually, or in a way or another, access to this conductivity, valley hole conductivity. So it seems good, but this doesn't mean that it's quantized as they promised, or that is topologically protected, or anything so far. So they also perform a last experiment where they measure this non-local resistance as a function of the length. They have a lot of arms in their sample, and they measure as a function of the length, and they extrapolate that, in fact, at 0 length, the value that they should have, given that this is an exponential decay, it's very close to the quantum of conductance of 2e squared over h. Which it's a way of seeing it. Why not? It gives you an indication that you might be in the right path. They have a critical a decay length of 1 micron also, which is pretty large compared to any other system so far. So now, that was the history until 2018, where a group in Japan decided to retake the same measurements, see what they could see. Okay, and right now they are making the same kind of experiments, but this time it's encapsulated graphene. So the quality of the sample is much better than the quality they had before. In the case of the previous experiment, the Manchester group, this was exposed to graphene, which is known to have a lot of impurities because of all the processing we do on the samples before they are ready to be measured. In this case, encapsulated devices are one of the best things you can have. Okay, so in this case, it's completely the opposite. So at the charge neutrality point, we have a very low resistance, while at the direct point, we have resistance of the order of 12 kiloohms, of the order of the quantum of conductance. So this is very puzzling, and they perform other experiments to know if this is really quantum valley hole effect. In fact, they made measurements using the Landau-Whittaker formalism for multiple terminals, and they realized that the longitudinal resistance seems to be very close of the quantum of conductance. The non-local resistance, they are not as close, but they are in the good trend, and they are all reproducible. They always have the same value. This might indicate that, in fact, they are measuring a valley hole state, a quantized valley hold state because of the ballistic characteristic of their sample. So interestingly, they try to measure the cubic scaling at low temperatures, the same we saw before, the way we know we can access the valley hold conductivity through the non-local resistance, and it was not, it do not fit at low temperatures where these measurements are taken. However, they recover the same behavior at higher temperatures of about 40 Kelvin. So this seems to go at least in the right direction. This means that when you decrease the temperature, you get into a ballistic regime, which might give you some quantization of the resistance, plus or minus some mesoscopic fluctuations. And when you increase the temperature, you recover the same kind of valley currents that other groups observe. By the way, this is not the only group having the same results. There is also a very recent paper at the Cambridge group showing exactly the same results. So now, okay, I break inversion symmetry, and then I have this beautiful access to Berry curvature. Now what we're going to do is, or what they did is, they also break time reversal symmetry. They just apply a magnetic field until the valley Simon energy it's enough to, it's in fact larger than the energy gap. So they close the energy gap. And in fact, what they see is that this quantized plateau that they observed in the previous figure, in fact, the width in magnetic field, the magnetic field that it can sustain, it goes very well with 2 times the energy gap that they also extract by thermal activation regime. So this is kind of a recap of all that has been going on in topological valley currents in graphene and BN. Graphene align on boron nitride. Now the first question to ask is, what's the effects of the angle? What is the angle doing in all this? Because obviously the angle between these samples, which is quite large, is around 0.8 degrees, is not at all the same of the angle of the Manchester group, which was closer to 0.2 degrees. So in fact, there is a very interesting theory about this, and that I just summarize it, extremely summarize it with this figure. This theory was proposed by Levitov and Justin Song a few years ago. They said that in fact, these bands are not topological bands unless they are at 0 degrees. Unless these 2 layers are at 0 degrees, because at 0 degrees, there is deformation of these solitones that I was telling you before. And in this case, and only in this case, the bands, the Berry curvature at the 2 edges of the bands, it's the same. And therefore, the Chern number of the band, it's non-trivial. It's plus minus 1, depending on the valley. In the case of simple moire, simple graphene on BN, close to 0, but not 0, we have opposite Berry curvatures in the 2 edges of the band, and that just following their calculation, that just gives you a Chern number, a trivial topology of the system. So I'm just gonna stop here, because this is kind of the full recap of monolayer. For tomorrow, we are going to see what happens in bilayer graphene, and hopefully we're going to see some beautiful results from our group too. So I will just like to stop here. So if you have any questions, now it's the moment.
Thank you, Rebeca. There was a question by Nasima, but
yeah.
Nasima, maybe you want to try to reformulate your question somehow? because I read through it, and it's difficult to understand, but it's really.
Yeah, I didn't get it very well. Sorry.
No, I tried also, and so I don't know. You want to try to reformulate,
Nasima?
or somebody else has any other questions? Okay, in the meantime, I have a question for you. Like, when you show those results where at 40K you recover the cubic dependence, but I assume that at 40K you don't have quantization, right?
Yeah, there is no quantization. They don't see quantization at 40K.
Okay.
Yeah, so it's only at low temperature at 1.5 K.
Okay.
So, yeah, and I mean, maybe I'm extrapolating too much, but they don't really show their temperature dependence. So I don't know. I don't really know, but I will assume that given the values, you can see, in fact, the longitudinal resistance, the maximum value at the satellite peak, it's too high for what they for what they say. Okay, let's say that it's about 10K, and for the case of 40K, it's more like 2K.
Okay.
Yeah. Okay. So there is no quantization, at least not of the longitudinal resistance. But I do agree that it's very possible in the fact that you recover the cubic relation after. So it's, yeah, I don't know. Not my experiment. You will see my experiments tomorrow.
No, I was curious to
yeah.
Just to understand. So there might be something else going on also at lower temperatures, right?
Yes.
From the cubic scaling, right?
Well, in fact, there is a recent paper. I think it's Marco Polini. I'm not sure, or Stefan Roche, or both, maybe. That they show that in fact you should change the regime. You should have just a cubic relation when you have a bulk conductance, because all this is just bulk conductance, and then you should pass to a linear relation when you have edge channels, when you have edge conduction. But this is not linear either.
No, neither. Okay.
Yeah.
Okay. Thank you. Yeah, I think Maxima brought his question again.
Yeah.
So the question reads.
Okay. Okay, I think I know what they meant. If not, just correct me. But yes, when you apply a displacement field in bilayer graphene, you also open a gap, break inversion symmetry, and you see the same kind of effect. That's what we are mainly talk about tomorrow. When you apply this displacement field, you break the inversion symmetry, you have this exactly same effect. K and K prime, they go in opposite direction, and it's the same physics of what we are explaining here. So break inversion symmetry, you recover or you have Berry curvature, and this Berry curvature is the one that is responsible for these valleys going in opposite direction. I don't know if that's what you meant. I hope so.
Okay. So then, if there are no more questions, I will thank Rebeca again for a very nice introduction to Valley Hall physics in graphene.
Yeah, and see you tomorrow.
And thanks to all the speakers and for everybody for asking nice questions as well. And yeah, we will see you all tomorrow at 2:30 p.m. Central European time.